Caleb, I went on a big rant at the beginning of this unit. When I introduced the concept of work to you, I said, work is not tiredness. Work is not tiredness. Work is force times distance. It's how much energy you put into an object. Power is tiredness. Power is how fast you're doing work. If you're getting tired, it's not because you're doing work, it's because you're doing work quickly. The word power, I wrote, is used in a variety of ways in everyday language. But in physics, it has a specific meaning. Power is the rate at which work is done. Anytime we're talking about a rate, that almost always means you're dividing by time. Power is work over time. Matt, work is what times what? So power is also force times distance over time, and it's also change in potential plus change in kinetic over time. But I'll write that one. It's a scalar. What are the units? What are the units for work? Joules. What are the units for time? But this is so important, we've given this a special name. Power is measured in watt.
Watts.
Power is measured in watt. Watts. Symbol capital W. And now we have, unfortunately, an equation that has a W in the equation and a W in the units. That's what we got. Need more letters in our language. We don't have them. If you're expending energy, it's not how much work you do that makes you feel tired. It's how fast you do the work, or how much power you generate. Power is what leads to tiredness. This is how stairs and other ramps work. You expend the same amount of energy. You do the same amount of work. MGH. But you take more time so you feel less fatigue. It's the difference between running up a flight of stairs and walking up a flight of stairs. You can walk up a flight of stairs and most of you won't even notice it. You run up the flight of stairs, you've done the same amount of work. Why are you huffing and puffing? Because you did the work quickly. Power is tiredness. So, a 60-kilogram girl runs up a flight of stairs 3.32 meters high. 3.32 meters, about one story, in 2.6 seconds. So think the stairs behind me over here in the corner, doing that set of stairs at about 2.6 seconds. Is that quick? You know what? That's brisk. Not really hustling, not really slow. I'm going to hit the stairs with a purpose, and I'm going to get up the stairs. You're not sprinting up the stairs, but you're probably moving your feet pretty quick up the stairs. Okay? What's her power output? What power is work over time? And in this case, I think the work is going to be the change in potential energy over time. I'm assuming she's going at a constant speed and there's no change in kinetic. So it's going to be mgh over time. Sarah, what's change in anything? So her initial potential on the ground would be 0. So that's why it's just mgh. Final, whatever, mgh. So how much power is this? Her mass is 60. 9.8. 3.32 divided by 2.6. What do you get? By the way, I also could have gone, Matt, work is what times what? And we've noticed the work done against gravity is force of gravity times distance. You still end up with mgh no matter which definition of work you use. What do you get? 750.751?
Yes.
Power is measured in watt? Watts. I picked these numbers on purpose because I wrote part B. If 1 horsepower, symbol for horsepower is HP, equals 750 watts, what's her power output? Almost exactly 1 watt. That's her almost exactly 1 horsepower. I wanted to give you an idea in some type of context of what 1 horsepower power is. It's around what all of you, because all of you weigh, give or take, around 60 kilograms. All of you, it's what you would expend doing that flight of stairs behind me over my shoulder in the back of the school here in about 2.5 seconds-ish. That's 1 horsepower. Most of you probably wouldn't even be huffing afterwards. Now, if I asked you to do it over and over and over and over and over, sure. I got to go on a bit of a negative rant here. James Watt is overrated. I don't think that there should be a unit named after him, especially one that is so fundamental to our electronic day and age, because watts show up in electricity as well. He was not that great a scientist. What he was a good promoter. People like to say he invented the steam engine. He didn't. He dramatically improved the steam engine. But what he was a good salesman. He had these steam engines, and he was going around to factories and to farmers and trying to talk them into buying his steam engine. And they would say to him, "What good is it for? What's it good for?" And he invented the horsepower. So when he says to a farmer, "This engine has 4 horsepower," what does the farmer think? This engine does the work of 4 horses. It doesn't. It has. They're not even close. But the farmer right away would then say, "Oh, okay, so I need 4 horses to get that much done. Oh, okay, it's worth me buying this motor." It was a great promotional gimmick. How good? We still use horsepower. Angela, do you have any idea how much work a horse can get done? No one does. Like a car, 260 horsepower. What the heck does that mean? With no idea in today's context. But it stuck. So, if I give you, yeah.
How did you figure out like the 750 watts?
The horsepower was invented before the watt.
Okay.
So really you're asking, why is a horsepower as big as it is? I have read that he watched draft horses that were, don't write this down, turning, so here's the horse, turning some kind of a round grinding stone in a circle, and he watched them and estimated how much they could get done in an hour, and that is sort of where he derived the unit from. I've heard that. Honestly, I'm guessing it was mostly made up as just kind of I need to sell some engines. I need to do some more research. If I give you something in horsepower, I will give you the conversion factor. We have it on this page right now. So, example 2, how long would it take a 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? What's this question asking me to find, Mitra? Time. Do I have an equation that has power and time in it? How would I get the t by itself? Where is the t right now? Ugh. Yes? And then how would I move the p over? So, time is going to be work divided by power. Now, the power in this instance is 5 horsepower. We don't do physics with horsepower. What was the conversion factor? So I think it's going to be times 750 watts is 1 horsepower. So how many watts of power is a 5 horsepower engine capable of putting out? 3,750 watts. So it's going to be 3,750. No, that goes on the bottom, Mr. Dewick. 3,750 watts. How much work are we doing? Key word here, Mitra, is the word lift. You could underline that if you wanted to. When you lift, which force are you doing work against? Which force are you doing work against? Gravity. Matt, work is what times what? Which force? mg. Which distance? h. Which in this case is 30. So let's put the mgh there. And now we can crunch the numbers. It's going to be 500 times 9.8 times 30 divided by 3750. You get 39.2? And that's time, seconds. Mr. Dewick, what if I needed this moved in 20 seconds? It's impossible. You need a bigger engine. And that's really what you would use this. You would use this to, so let's go take this on a bigger scale. The big cranes you see on the skyscrapers in Vancouver, you would actually be able to calculate how many kilograms they're able to move per hour, and you could use that as an estimate for how long it's going to take you to bring in the beams and bring in the girders. And you can't go any faster than the horsepower or the wattage that your engine is capable of putting out. You can't, because there's a T in the equation. There's another way to calculate power. Power is work over time. Matt, work is what times what? So I wrote that here, and then I'd like all of you to circle that there, the D over T. Kevin, what do I measure distance in? What do I measure T time in? Yeah. What? I got to be really, really fussy, not a velocity, because we're in Scalarville. Another way to calculate power is also force times your average speed, which if we're going at a constant speed will just be your speed. It's not blatantly in the equation. It's kind of hidden there. Although, did I give it to you this year? I can't remember. I know I thought about it over the summer whether I was going to give you this. I used to make my kids derive it from power equals... Wow. F times V. There it is. You're the first group that I actually gave that to. When do I use that? If they're asking how much power and they don't give me work or time, but they give me a speed. You'll see one where we do this later. So power is work over time. It's how fast you're doing work. It's the rate at which you do work. It's tiredness. Efficiency means, well, how much bang do you get for your buck? How much useful work do we get out as a fraction of how much work was put in? How much energy do we get out as a fraction of how much energy we put in? There is a Greek letter as a symbol for efficiency. It's the Greek letter eta. It looks like a lowercase n with a droopy tail. Although I only found out that eta was the symbol for efficiency a few years ago, I also just used to just write EFF as my abbreviation for efficiency. Whatever you use, here's how you calculate efficiency. It's work out divided by work in. Or energy out divided by energy in. Or power out divided by power in. This will give you a decimal, and then you want to change it to a percent. How do you change a decimal into a percent? If you times by 100. I don't remember that. I've given it to you, but I don't remember that formula. First of all, part of it is it's tricky. I have a specific question in my mind. I like this question, I like this question, I like this question. That you're going to see when we get to electricity, because in electricity, appliances have wattages, they must use power. And there's going to be a question that's worded in such a way that the word out happens to show up right next to the amount of power you're putting in, because of the outlet. And the word in happens to show up right next to what you're getting out. Okay? So I get this mixed up all the time, so here's what I remember. On the right-hand side, efficiency is always smaller number divided by the bigger number, and then times 100%. And the reason is, I'm sorry, the law of conservation of energy says you can't have efficiency more than 100%. If you did, Angela, you're getting free energy, and that violates the law of conservation of energy. So what I do is I first of all make sure the units match. I'm dividing joules by joules or watts by watts, never watts by joules. But then it's always going to be, it's the smaller number divided by the bigger number, times 100%. So I wrote here, efficiency is always less than 100% unless you plan on winning a Nobel Prize. If, by the way, Lena, you did actually invent something that was more than 100% efficient, the fancy phrase we say is that was over unity, and you weren't doing crap science, because there's a whole bunch of people out there that claim they have free energy machines. Do a YouTube search and take a dive down the conspiracy theorists. If you did actually invent such a thing, if it was possible, then about 10 years you'd be able to buy Bill Gates and Jeff Bezos and Facebook all in your sleep. You'd be the wealthiest person on the planet. Because if you give us free energy, even with our current technology right now, Sarah, without Star Trek technology, without fancy schmancy, if you just give us free energy, just with our current level of technology, there is very little we can't engineer our way out of now, just with our level of technology. Oh, we got people going hungry, we got world hunger, we got free energy, let's put lights all night so we can double our vegetable growth. Bada bing, bada done. Oh, very few things. I would certainly deal with climate change. Who needs fossil fuels? Put one of those in every car and the car will never stop driving. Don't need to burn any gas. Done. So, but Kevin, don't waste your time looking. The law of conservation of energy says it's not possible. Typical household light bulb transforms energy at the rate of 60 watts, 60 joules per second. Most electrical energy, unfortunately, is transformed into heat instead of light. About 57 watts of heat and only 3 watts of light are produced by the lamp, so an incandescent light bulb is only about 5% efficient. Usually, the more heat you're moving around if you're an electrical appliance, the higher your wattage. So an electric kettle is usually about 1,500 watts. Microwave is usually about 12 to 1,300 watts. Stove, considerably more. The two biggest are usually your dryer and your stove. Hot water heater moves a lot of heat around as well. Those are usually pretty high wattage. I got to go on a bit of a rant with the light bulbs here. So our Canadian government a few years ago has passed a bill, incandescent light bulbs, the ones that you twist in, the old ones that you grew up with that gave off a lot of heat, are being phased out because somebody said, well, they're terribly inefficient. Now, it is true, incandescent light bulbs are terribly inefficient when they're in your house. They give off a lot of heat. But that heat isn't wasted. Your parents' heating bill is lower by exactly that amount. It's not a wasted amount of heat. So this was some well-meaning, poorly thought-out science. Now, you might say, well, Mr. Dewick, what about outdoors? That's wasted heat. Those spirally CFC ones that you spill, how well do those work outdoors? Not well at all. They don't deal with water very well, so they don't work well outdoors. You might say, Mr. Dewick, I agree that heat is useful in the winter, but I don't want the heat in the summer, so I should have those CFC bulbs in the summertime. Spencer, what country do we live in? In Canada, do we have more daylight or less daylight in the summertime? Do we use light bulbs more or less in the summertime? Way less. And the other issue with those spirally CFC bulbs is they contain mercury. And those, they have to be, by the way, I'm telling you this as a science nerd, if you have any of those spirally CFC bulbs, you know the ones I'm talking about? They're the same, I was going to point it to the same style as those used to be. Now those are all LEDs. But you twist them into a regular light socket. Do not throw those into the trash. Please take them to Maple Ridge Recycling and recycle them properly. The mercury in there, if you throw them into the trash, ends up in the water system, ends up in the water table, ends up in the ocean. And despite what I said about if we had free energy being able to solve most of the world problems, I should have taken that back. We don't have the technology and probably never will have the technology to remove all the mercury that we've dumped into the oceans, which have now made their way up the food chain into the fish that we eat and are now getting back into us and poisoning us. So, let's do a question. Example 3. Point being, it was some well-meaning science by politicians who didn't think things through very well. LEDs are probably the future, although now I'm reading there's some issue with the frequencies of light that those give off, but Such is life. Kyle, what does A want me to find? Matt, work is what times what? Is there a force? Is there a distance? Definitely a distance. Oh, Matt, underline the word lifted. Whenever we see the word lifted, which force are we talking about? Okay. Work is going to be mgh. It's going to be 250 times 9.8 times 12.5. 12.5 meters, about 3 stories. Actually closer to 4 stories. 250 kilogram mass, that's a 650 pounds. So that's pretty heavy. What do you get? $30625. And now if I go to 3 sig figs, how about 3.06 times 10 to the 4th joules? I'll even bring out the scientific notation there. B. Lyndon, what's B want me to find? Power is work over time. Did they give me a time in this question, Lyndon, my friend? Power is force times average speed. Did they give me an average speed in this question? In fact, is it a constant speed? Oh, even better. What force, Lyndon, my friend, are we lifting up against? So it's going to be 250 times 9.8 times 2. I think I can do that one in my head. 250 times 2 is 500. 4,900. Double check my math. I think I'm right. 4,900. Lyndon, powers measured in watt? C. Manir, what's C want me to find? So efficiency. Now I notice they're talking in part C about power, so it's going to be power out divided by power in, but really what I'm thinking is it's going to be the smaller number divided by the bigger number. Here's one amount of power that I have, and I think that is what I got out, 4,900. Here's another amount of power that the question gave me, 10 kilowatts, 10,000 watts, and I think that is how much power was put in. Yeah. Yeah. Did they give me a time? So, power is work over time. Did they give me a time? So we have to use another equation for power. What was our other equation for power? That, and by the way, that's my process. I always try work over time first. Yeah, no, that's okay. I always try work over time first. No time! Did they give me a speed? Oh, use that one. The one with the speed in it. Anyways, Manir, I'm pretty sure it's going to be 4,900 divided by 10,000 and then times by 100 to make it a percent. And I think you'll, because I can do this in my head, I think it's 49%, isn't it?
Yeah.
Where'd the other 51% of the power and 51% of the energy go? Heat, sound, dissipative energies? Yep. By the way, just that there, this is probably an electric motor because gasoline or internal combustion engines are notoriously inefficient. They're usually in the 20s. So just seeing that 49%, I'm betting this is, although electric motors are usually more efficient than this. Example 4. A mass of 100 kilograms is pushed along the floor at a constant speed of 2 meters per second. Lena, my joy, what's example 4 asking me to find? Power. So the first thing, Lena, I would write, power, is work over time. Read the question, Lena. Did they tell you a time in seconds anywhere? Also, I would say work is force times distance. That the top part. Did they tell you a distance in this question anywhere? What's my other expression for power? That's not the full expression. Can you go back one page and find it in the box? Force times V. Did they give us a... By the way, I got to be fussy. It's not a velocity. Speed, because we aren't scale. Did they give us a speed? Okay, so I'm already leaning that way. What force? Well, the fact that I see mu, this is a job for, let's do that over here. What are the forces acting? We have mg down. Normal force up. Now, the force that we want to find is the applied force. I don't know the applied force. What's the two-word key phrase, though, in this question that helps me figure this out? Okay, so constant speed means, Lena, there has to be a force the same size as the applied force pointing in the opposite direction. What? I saw your lips move. What? Say it loud and proud. Yeah. So, Lena, don't write this down just yet. What I would be saying is, it's the applied force. Don't write that down. Except I don't know the applied force. Oh, but look. I know another force exactly the same size as the applied force. So I'm going to write friction. Again, I got to point out, it isn't actually the friction force creating the power, but I know it's the same magnitude because of constant speed. Friction is what times what? Mu times the normal force times V. I don't know the normal force. Oh, but look. Another force the same size as the normal force. Mu mg times V. Nice. Do I know mu? Do I know m? Do I know g? 9.8. Do I know v? Hey, here we go. So it's going to be 0.25, 100, 9.8 times 2. 490? Power is measured in watt? Power is measured in watt? 490 watts. Is that right, folks? Yeah. Okay. Braden, what do you see after the kilograms? What word do you see after kilograms? Lawnmower question. Okay, but I'm already seeing there's probably going to be a free body diagram with the force either going up at an angle or down at an angle. Did I say angle? This is going to be a job for... Okay, we can do all this. I think before we dive in, this is going to be a job for a free body diagram. So, here's the lawnmower. What are the forces acting on it, Braden? Get the obvious one. I don't know yet. Hang on. Is there an angled force in this question? Deal with that before we do the normal force. It does say pulls on the lawnmower. If they had said pushes, I'd have the force going down, but they said pulls, so I'm going to have the force going up. This is 25 newtons. That's the applied force. What's the angle theta? Did I say angle? And the reason I want to do this first is this is going to help me figure out, what do we call this one here? F what? Fx and Fy. This is going to help me figure out, Braden, whether normal force is bigger, smaller, or the same size as mg. Smaller. And I might not have spotted that if I had jumped straight to normal force right away. What else? Okay. Braden, what's A want me to find? It's not what A wants me to find. That's what B wants me to find. A is the letter that looks like a little circle with a vertical line next to it. Usually it comes before B. That's the tendency anyways. What does A want me to find? Matt, work is what times what? Braden, did they give me a distance in this question?
Yes.
So I'm leaning towards force times distance. Which force? So you're telling me it's going to be 25 times 4.5? Even if friction wasn't there, I'd still have an issue with it. Why can't I use that 25? Because the force and the distance are not in the same direction. What's the force that's in the same direction? Huh? I think the work the person does is going to be that. Now, Braden, that's the total work this person is doing. Some of the energy is going to go into overcoming friction, and only some of it will be left over for whatever lawnmower. FX. Adjacent. Hypotenuse. Which trig function for Fx? So this is going to end up being the applied force cos theta times d. 25 cos 15 times 4.5. How many joules of work does this person do? Huge difference. This is the applied force, the slanty. Fx is the horizontal component of the applied force. And that's why it's F applied cos theta. What do we get? 25 cos 15 times 4.5. 108 points, and then 4 6s and 3 5s, and probably yuckiness. I'll go 108.7. Well, actually, I'll go 109, but I'll keep this on my calculator. Or I'll jot it down here. What was it? 108.46s. I'll do 3 6s and a 7. That's 7 sig figs. That's got to be pretty good. Okay. Braden, what's B want me to find? It's going to be the force of friction times distance. Friction is what times what? Mu times the normal force times distance. I don't know the normal force. Normal force is Fy? FYI, I think you're wrong if the normal force is Fy. Oh, so you're saying everything up equals everything down? How'd you get the normal force by itself then? Mg minus Fy times d? Okay. Which trig function was Fx? Cos? Which trig function do you think Fy is going to be? So it's going to be mu bracket Mg minus, and Mitra, there's F applied sine 15 times d. Let's plug and chug. Mu 0.1 M. What the heck was M? 20 times 9.8 minus 25 sine 15 times d. How far do we move? 4.5. How much work did friction do? $85.2882, 85.3. Why must that be wrong? Because it is. Got to be a negative because the force and the distance are in the opposite direction, right? We lost energy. How would I show an energy lost? Negative. What's C want me to find? Time. could probably solve this by calculating how much power there was and solving for the T in power. I wouldn't. Could. I think, looking at what I found, Lena, do I have an expression for the force of friction here? I got it kind of tucked away in that bracket there. Do I have an expression for the for the Fx? Yeah. I think I'd go winner minus loser. I'd go Fx minus friction equals ma. Get the a by itself. Vi is 0, and I can find t. Oh, d is 4.5. And I can find t. That's how I would do it. So I'm going to say this. Wow, I'm getting the yawns here. This is the last one. 2 more. Cool. Person pushes with 85 pushes, I should underline. With 85 newtons on a lawnmower, which has a handle angle of 25 degrees. Mass of 20 kilograms. Surface is 0.15, 40 meters in length. Mower starts at rest. Find the final speed of the lawnmower and find the rate at which heat energy is generated. Don't cross it out. I'll do that one next lesson. I want to get to example 8. Did I miss example 7? Yeah, I nuked it. Also, example 6, this is tougher than I would ever ask you on a test. It's even overboard for a nasty multiple choice question, to be honest. Example 8. On a stair climber at the gym, a 75 kilogram person lifts their center of mass up 22 centimeters with each step. They take 360 steps in 6 minutes and their muscles are 18% efficient. Find the rate at which the person does work. What the heck is A asking me to find? Oh, power, because that's the rate at which work is done. That's how I defined it. I have 2 definitions for power. Work over time or force times speed. Matt, do you see it? No, sorry, I'm coming back to you for the other one. Spencer, do you see a force or do you see a speed in this question? Let's try going work over time then. Matt, work is what times what? On a stair climber, which force are you doing work against? This is going to be mgh over time. What's M? What's G? What's H? Careful. 0.22 is wrong. 0.22 is wrong. It's not 0.022. Lyndon. What? Not 22 times 360. 0.22 each step. How many steps? That's the height change that he's going or she's going through. Put your calculator down. Clear your calculator. Just write 0.22 times 60. Divided by, what's the time? 6 what? How do I change minutes to seconds? Oh. Mr. Dueck, what meneer? Is there a 60 on the top? Why, yes, there is. Is there a 60 on the bottom? Yeah. Are there plus signs anywhere, or is it all being multiplied? Then you can cancel. So type this into your calculator. 75 times 9.8 times 0.22 divided by 6. This is what, if you've ever used an exercise machine that has a little clip that you can put on your finger or whatever, and it tries to estimate your how many watts and then your calorie count, but this is ridiculously inaccurate. Because the ones on your machine usually don't have your mass entered in, unless the machine is a higher end one and it has a built-in scale, which most of them don't. Yeah.
Sorry. So wait, what happens to the other, like, it's 360 steps. So what happens to the other?
Oh, times 60. Should be times 360, Mr. Dewick. Why did I go times 60? I'm sorry, folks. Times 360. And then you can say, you can cancel out a 60 if you want to. There's a 60 hidden in there. I'm sorry. You can do that if you want. There is force times distance divided by time. Force mg, distance, 360 steps, 22 of them, divided by time. What do you get? $161.7, which I'll call 162 watts of power. What's the rate at which you're using food energy? What else has this question given us that we haven't used yet? Efficiency is going to be power out divided by power in. Is B asking us to find the power out or the power in? Ready?
That's the pout.
Is B asking us to find the bigger number or the smaller number?
Smaller.
The good news is one of these guys is right. Here. If we're looking for the smaller number, that would somehow say that I had
No, I'm trying to say like, and then.
okay. So I think this is asking us to find power in. How would I get that by itself? Where is it right now? How could I fix that? Multiply it to the top? Oh, and then that would end up down there. It's going to be 161.7 divided by 0.18. $898. Okay. That's how many watts of power this person generated, how tired they would get. If you were in better shape, your body is more efficient. So that means that this number here, that 0.18, would be bigger or smaller? Bigger, which means this answer here would be, that's why people in better shape don't get tired as fast. I mean, which you all know, but there's the physics equation that explains that. Yeah, of course not. Your body's more efficient. What's your homework? Try it. Number 1. Number 2. 3 is good. 4 is good. 7 is good. 9 is good. 10 is good. $11. Not going to be any homework next class. Meh. 14.